And now we've got a few components of that general equation. First of all, let us take the conservation of the angular momentum. After integrating an integration constant appears here, which is denoted by L0, and can be interpreted as the angular momentum at the, let's say, inner edge of the disk, but let me say at that moment that we do not assume any inner edge of the disk. This is, let's say, the limit to which the angular momentum profile approaches. We can take the diffusive form of viscosity or approximate it using the alpha p prescription, which is quite useful because technically speaking, it's much easier to obtain a converged solution of such a problem. Another equation is the conservation of the radial momentum, which was not considered by, let's say, for example, Novikov and Thorn, and this is its final form. As we see, we take the radial gradient of pressure into consideration. And let us move to vertical structure. We have to assume some kind of vertical equilibrium to close that set of equations. And in general, to do it properly, we would have to solve the vertical structure of the disk. But it's quite complicated, but I can say that we are working on this, or at least we are starting to work on this. But in this problem, we have to assume, we have to impose some assumptions about the vertical structure of the disk. And for example, at that point, if we assume some particular profile of pressure in terms of vertical coordinate, let's say theta, then we can, using that form of vertical equilibrium, you can get some formula which lets us calculate disk thickness h in terms of the other quantities that are there. We consider also the energy balance, and as I've already told you, we don't assume that all the heat generated by viscous processes is radiated away. There is also some advective flux, which is described by that expression. To calculate the flux generated by viscous processes, we take these formulas using alpha p or diffusive form of viscosity. And once again, to calculate the outcoming flux of energy, we have to assume something about the vertical structure. To do it properly, we would have to perform a whole general radiative transfer in the vertical direction. However, to simplify the problem, and so far we assume that the disk is optically thick, and we assume diffusive approximation, which gives the formula we've got here. These are all equations that are necessary to be solved by some not straightforward but all algebraic transformations. We can put all equations into a set of two differential equations. Let's say for the radial velocity v and for temperature. And this set of ordinary differential equations has this feature that there are fractions. The denominator of this fraction vanishes at the point where more or less where the radial velocity is equal to the speed of sound. So we've got some kind of critical point which we say is the sonic point. And to obtain a solution which is physical, we have to make sure that at the same point where the denominator vanishes, the denominator must also be zero. This is what nature requires. So the problem is not so simple. It's not enough to put on some boundary conditions far away from the black hole, then integrate inward. It's not enough. We have to choose a proper value of that angular momentum close to the black hole L0, which I showed you a few slides ago. Such value which which makes sure that the denominator disappears at the same time as the denominator. In fact, technically speaking, this is a two-boundary value problem. We have some boundary conditions far away from the black hole, and we've got two boundary conditions close to the black hole, which are connected with vanishing of the denominator as well as the denominator. And to do it, we apply a relaxation method of solving such a problem, and we get solutions. Now let me go to less boring part of that talk, and I will show you a number of figures. So first of all, let us look briefly what the solution looks like. The red line is for this model that for the solution that we get. The dashed green line is for inner solution of Novikov and Thorne approach. This is valid, that green light is valid up to 30, 40 gravitational radii. So as you see, the disk thickness is increasing, and beyond 10 gravitational radii, the H over R ratio is almost constant. We see the distribution of the surface density, as well as the central temperature and the flux. And for the applications that I'm going to talk about in a few minutes, the flux is the most important thing, because it can be used to estimate spin of the black holes that we observe, as well as it has that important feature that it does not depend on the viscosity prescription we consider. So let us look in detail onto that flux profile. The red line is our solution, which goes beyond the inner stable circular orbit, while the blue and the green dashed line are for Novikov and Thorne approach. So when we look at let us look at the Novikov and Thorne solution, which uses exactly the same assumptions as we do. And for very low mass accretion rate, we see that the flux almost coincide. I mean, the red line is almost exactly like the dashed green line. But when we look at higher mass accretion rate, which corresponds almost to the Eddington luminosity, we see that our solution is different than Novikov and Thorne. And this is because for high mass accretion rates, the advective flux, the energy advected inside an accretion disk is quite significant. And the result of that is that the energy is not radiated far away, but is taken inward and finally radiates closer to the horizon, or is swallowed by the black hole. That's to see what is the influence of that advective flux. Let us look at that advection rate, which says how much energy is not immediately radiated away, but is advected inward. And we see that the most important thing is that for the higher mass accretion rate is the higher advection coefficient is. But one more interesting thing is that the limit for low mass accretion rate is not zero. It can be proved that it looks like this, but as we saw at the three plots ago, that rate of advection rate is not significant, because the fluxes looked quite similar. And let me now entertain you with some animations showing the influence of various parameters of the system on various profiles. So first let us look at the dependence of the radial velocity of the disk versus mass accretion rate. The mass accretion rate starts at 0.01, which is quite low, and goes up to 0.99. And as you see in some particular range of mass accretion rates, there is some characteristic non-monotonic feature in that profile, which is being investigated. Let me say like this. This is the radial velocity. The surface density corresponds to the radial.
For what kind of spin?
This is for zero spin, and in a moment I will show you what the profile changes in terms of black hole spin. The surface density is connected to radial velocity with by that mass conservation equation, and you see a peak in surface density which corresponds to that feature I told you about in the profile of radial velocity. Okay, let us look at the flux and in which way it changes versus mass accretion rate. As one could expect, the higher mass accretion rate is the higher flux is, the higher amount of energy is emitted from the disk. Nothing more happens here. Okay, and let us look what is the influence of the black hole spin onto the disk profiles. The higher spin is, the closer to the singularity is the inner stable circular orbit, so that the whole profile moves inward to the black hole. And let us look on the flux profile. As on the previous plot, when we increase the black hole spin, it moves. The maximum moves inward, as well as the photons emitted become more energetic.
Is your horizontal scale, is it Schwarzschild radii, or is it mass? Because you had mass before, but then
I sometimes mistake them. Let us have a look. This is gravitational radii, so this is 2m, this is 20m.
So this feature you had is actually at 3m,
exactly,
not 6m. So it's within the.
No, it is at 6m.
So it's at the mergely stable orbit.
Mm-hmm.
Okay.
Yeah. Okay, and finally, let us point out the applications of such analytical, let's say, relatively easy spin disk relativistic disk model. So first of all, we would like to, and this is what we are doing right now, we would like to apply that stationary solutions of accretion disk to estimations of black hole spin. The point is that allowing for advection, we make us possible to go to higher mass accretion rates, and in this way we hope to improve the estimations that have been done using Novikov and Torl disk model, which is not valid for high mass accretion rates. This is what we are doing right now, and one more application that somebody can think of is that people investigate time-dependent solutions of accretion disks. The most important thing is that for some rates, some range of mass accretion rates, there are limit cycles in that time evolution of a disk, and to perform such time-dependent simulation in the Kerr metric, one has to provide an initial starting point for this simulation, which is got from the model that I'm describing right now. And we are also working on this right now together with people from Xiamen University. That's all. I would appreciate questions.
Thank you very much. Questions?
I'm curious as to whether that surface density feature or that radial velocity feature has anything to do with your chosen boundary condition on L naught.
No, not at all.
It doesn't. Okay.
No. Actually, the solutions are completely insensitive to outer and boundary conditions because they converge very quickly to the proper solution. So.
Oh, sorry. So L naught is associated with an outer boundary
No,
condition.
you mean the
Also,
L,
Yeah.
the
L0,
inner
yeah.
L0? Okay, but
Yeah.
L0 is we have to L0 is determined by that regularity conditions at the solving point. So I cannot impose it.
Oh, I see.
I
Right.
get it out of the code.
Is that feature comparable in size to the scale height of the disk? Smaller? It seems quite sharp.
It seems sharp, but remember this is the surface density. This is a feature in surface density. We don't see it in disk height, disk thickness at all.
Because
No,
we
but-
want but I'm asking the radial, is it radially the same size as the scale height?
let's show the graph
Mhm.
again.
Let's let us go back. It happens at 3 gravitational radii, and at it depends on the mass accretion rate. But I'm not sure if I understand the question. But the h over r radius for, let's say, 0.5 mass, adding to mass accretion rate is 0.1, 0.2.
So it is comparable but
Comparable.
larger.
Yes.
You showed the radial velocity in the limit of vanishing m dot, right? Or what was the quantity where you had 10 to the minus 5 for the m dot, and
10 to minus 5 was
one of the previous pictures.
used only.
you
for
were
the-
saying that this curve does not converge to 0. It's different from 0.
This is not radial velocity.
No.
This is
Oh, that
the
was it.
ratio of
Oh, I see.
effective as
I see.
the energy advected versus emitted.
Yes. So does this value, I mean, you get a wiggle around some value. Do you think this value makes sense? I mean, from theory or why did?
I
what's the
have
reason?
to say not yet,
Uh-huh.
but I hope. Well, it can be done, and I have to do it to check if I get proper solution.
Because obviously your derivatives are not calculated correctly with this wiggle, right?
Well, this is some kind of technical thing concerning relaxation method. If we impose wrong boundary conditions, then we
yeah.
get some kind of zigzag. But we can say that the average of this zigzag is the proper solution.
But that needs to be verified. I mean, I know situations where that is not the case. It's very some surprising cases happen when the wiggle is not converged around the correct value.
But the question is, what is the correct value?
Yeah, exactly.
So there are, of course, technical
Mm-hmm.
problems
Mhm.
which Oleg mentioned.
Mm-hmm.
But there is one thing here of a more kind of fundamental nature. And that the thing is that, strictly speaking, Shakura-Sunyaev or Novikov-Thorne solutions were obtained in the limit m dot equals 0, because they are for very thin disk.
Mm-hmm.
They, of course, haven't considered advective flux at all. The advective flux is artificially put to 0.
Mm-hmm.
But then you can, having their model, check for consistency. What is, because you know everything. You know the run of temperature, you know the run of radial velocity. So therefore, a posteriori, in Novikov-Thorne, you can calculate the advective flux, which of course is non-zero. That is a trace of this. That in this limit m dot going to 0, in Novikov-Thorne, there would be non-zero advective flux, calculated formally from their solution. So that is nothing special in the fact that in the limit m dot equals 0, advective flux doesn't go to 0.
And it comes out from the fact that
Yeah.
advective flux is proportional to radial velocity, which goes to 0 for m dot going to 0, as well as the flux emitted is proportional to m dot. So we've got 0
Yes.
over 0,
Yes,
probably
yes.
it is not
Right.
zero.
Mm. Right.